Hello, all. We are going to be starting today by looking at the following example. So, we're going to try and prove the following statement. Um, and as a reminder, we're just going to write this out in words so that we don't get lost in what each of these terms mean. So, let's do some color highlighting here just to help us out. This first here is telling us that we're saying for all m greater than 0. Next piece here is telling us, in orange we'll do, there exists a value of n greater than 0. And in that last little piece here, we're going to go with such that n is going to be less than mn squared minus 1. That's what we're going with here. All right. So what we're saying is there must exist some value. Well, we're trying to prove that there must exist some value of n greater than 0 such that the following statement is true. Now, as a reminder within our class, if we're not going to put what the number space is, so if we don't actually say if it's integers, if it's natural numbers, if it's the reals, if it's reals, positive, we're going to make an assumption that we are working within the real space over here. So we are assuming that m is an element. Well, yes, we're going to assume that this is what we're expected to solve for, where m and n are going to be elements of the real number space here. So when we're looking at this from the mathematics perspective, there are two things that we have to kind of consider, because from a computer science perspective, pardon me, we end up not really caring about one of the two spaces quite as much. Um, but from the mathematical perspective, we're going to very quickly realize that m can take on a value that is between 0 and 1 or is greater than 1. And we're going to see how these two different cases potentially affect our proof, which we care a great deal about when we're trying to prove this from a mathematical standpoint of the statement being true. So, a couple of things that I noticed right off the bat when I'm reading this that help me sort of find that intuition for where to go next. The first thing that I notice, and these are just things that I noticing stuff. We're gonna have to come up with like a sting for whatever these are gonna be for us. The first thing that I notice is that we define m before n, and a reminder that we're trying to actually pick a value of n. Our goal is pick an n. And so what this does is, again, if we're going to talk about it from the computer scientist inside all of us, this is kind of like saying in our program, the first thing that we would do is we make a class. Let's just talk Java for a second. Class A. And we define some variable. I'm just going to make it, well, I guess technically, because we're going to be in the reals, I'm going to make it a double m. And it has some value. I don't know what it is, but I know that it's been declared and initialized. Declared and initialized. I can spell. And then what we're going to do, I'm actually just going to shift this over so that I don't run out of room here. There's no reason for it not to be shifted over. We're going to have like maybe some other code. And at some point we come across a function or a method, public static void prove statement. It's going to be the statement that we're working on. And inside here, I end up with this double n. And we need to give this a value in order to write the rest of our code, because if we look at the statement that we're trying to prove, it does use n. Now, so we do need to give it a value of n before we can prove it. Now, we know that m already exists because we defined it at this global level, and it came first in our sentence, which is why I'm allowed to declare that at the global level. It could also be declared more locally, but point being, it's the very first thing that happens inside that proof statement method then. So I just sort of treated it to be like at the global level, saying, yeah, this was definitely done before we called proof statement. And this is important because it means that we're allowed to use M when we're trying to define N. And we might find that that's going to be really important. So the first hint for me is that since this was set up like that, I probably will need to use N. And this is further solidified by me noticing one more thing. The second thing that I notice is how closely tied M and N are. We don't end up with something that we've seen previous in the course where it was more like, n squared plus M or n squared plus M cubed or whatever it might be. That's like addition of the two different values that make it really easy to manipulate. What we notice instead is that M is going to be quite closely tied to some kind of N value over here. So we might actually need to relate M and N in our value of existence of N in order to move forward with this proof in a good way. Okay, so that is the two things that I noticed. And now that we've noticed a couple of things, we can start to actually do some of the background work. Now, some people are going to call this their scrap work or the background work. This is kind of all the real work that we do, background work. Now, when you submit an assignment, when it comes to this, when you submit a paper, this background work all gets factored out. We kind of ignore it. We just submit the really polished solution that we're going to see right at the end of all of this. But in theory, this is where all the real work is happening, right? It's happening in the background, not in your official, here is my proof. So we use this to kind of get to our final place. We figure it all out, and then we can roll back our background work all the way back up to the top to get our final answer out of this whole thing. So when we're dealing with factor exponents of n, we have two things that we need to consider here. I'm going to pick this up, and I'm going to bring it back down here. Now that we're looking at this again, I'll do that one more time when we get to our official proof. I guess I can leave that in because that part is still just true. All right. So the first thing here that I'm going to consider is this -1 right over here is gross. It's not helpful. This -1 is bad news for us. I feel like I should put it in like a green because it's like green for disgust, like in the Inside Out movie, and be like icky -1. And if you're asking yourself, how do you know that this is icky, Lauren? How is -1 problematic? Well, I can answer that question pretty easily. For one thing, it's going to be a problem if n is small. So remind ourselves here that n is in the reals, which means that n could be 1 or 2 or 3 or 4 or whatever, but n could also be a decimal value. Yes, it could be a decimal value greater than 1. It could be 1.5 or 2.17 or whatever, but those become less of a problem because remember that this decimal value here, something that's less than 1 in a decimal value, that's like a really tricky area for us to be in. Let's pretend for a second that that is indeed the case. We're going to say that n is equal to 0.5 for just a second. This is just to sort of show why this is icky. This isn't really part of our scrap work. This is more like the intuition here. If we take 0.5 and we multiply it by 0.5, I'm doing that because of our n squared right here. We're going to end up with 0.25, right? 1/2 times 1/2 is going to be 1/4. So we take a half and we multiply it out and we get a smaller value. That's really, really important here for us to remember, because when we do something like that, even with n just being 0.5, we run into this issue, but getting smaller is going to be key here. When we do something like this, we're going to end up with a negative number, right? We end up with negative 0.75. Negatives, when we're doing this stuff, we don't want to deal with negatives. We know that all of our values here need to be greater than 0. We want to avoid negatives at all costs. So by looking at that intuition, by looking through that, I can say, oh yeah, this -1 is definitely going to be a problem for us. It's okay if it was 1 minus something else, that would keep us positive. But when we're in that less than 1 space, this becomes a huge problem for us. So the first thing we're going to do is we're going to try to get rid of that. And we do so by factoring n squared out. And this is a trick we're going to come back to over the course of the next couple of videos as well. This idea of factoring out that largest exponent value of n, of what we're looking for. So let's go ahead and do that. Let's see. We started out with this. Oh, I'm going to switch colors. Sorry, I didn't mean to stay in my icky -1 color. We're going into our scrap work here. So n minus, there we go. We're going to factor n squared out of this, as we just said. And so, oops, sorry about that. Put that back wherever that was. It was like there. Okay. So what are we going to do? We're going to factor it out. That means we end up with n less than, take out that n squared. This allows us to shift that 1 to the other side. And now we do this. So just notice again that if we were in that situation where we said n was something like 0.5, having a quarter on this side is not a big deal because 1 minus a quarter leaves us still 3/4. So we're going to stay positive. We've now shifted the 1 to the other side in a really sort of elegant way. Now, personally, I found this whole term right here to be super confusing. So as we go through this, I'm going to end up actually doing something with this, again, computer sciencey, to help my own self, and I hope it helps you as well. So now that we have this, we can ask ourselves, what else sort of can we get rid of to make this simpler? And again, we want to, right now, we're trying to find a value of n, right? That's our goal right now is, does, we know it does because we're being told in this example to prove it, but, what is the existing n value, right? What actually is that going to be? What is it that we are trying to find? So let's try and find an n value. So right now we have an n over here, but we have an n squared that we still, it's kind of annoying. How can we deal with this? If we divide n, we'll end up with a single n over here. But if we're going to do a division, not just a factor, but like an actual arithmetic operation to one side of this inequality, we do have to do it to both sides of the inequality. So we're going to say divide by n. And when we do that, we're literally going to divide this whole thing by n. When we do that, we'll notice that n is greater than 0. Thank goodness, we don't have to worry about any negatives. That means that our inequality stays the same. 1 less than. And if I divide this whole term here by n, I can just take the n right out of this n squared. All right. Cool. So we're definitely heading in the right direction here. So now we only have a single point of contact where n exists. And I hope I know what you're thinking. I hope my intuition here isn't wrong in terms of getting in the mind of somebody who doesn't know math, because I don't know math. I genuinely don't. This is like my 6th time solving this problem so that I can really get a strong understanding of what's going on here. So I'm not saying that just to make you feel better or potentially make you feel worse. I really don't. It's not my strongest suit. So that's for real. So we have this single n here now. It's only in one place. And the reason why I'm saying that we don't need to worry quite so much about this n squared, and again, we're taking this from the perspective of a computer scientist. And we look at this right here as a single term, 1 minus n squared. And if you recall, one of the things that I was concerned about is when we pick that n to be in a really tricky space of like 0 to 1, this could be a problem for us. It's not a problem for us if n is big enough, right? If n is a large number, we're going to stay positive. If n is a really small number, we need to make sure that we find a way to keep this whole thing positive. We don't want a negative number over there. So since we're going to be kind of treating this like a unit, and my brain is so computer sciencey. I'm just going to make up a new variable for a second and stick this whole thing inside of it. So then I can say that 1 is less than m, like this. And that's just for my own brain's clarity. If this is more confusing for you, instead of an x, keep this whole factor in there. That's totally fine. You can keep this whole thing in here instead of an x. You'll just replace it everywhere you see my x. But for me, I found this to be helpful as I move through these last few steps here of determining what this value should be. And now I want to solve for n. And the best way to solve for n, solve for n, I don't need to say is, but solve for n by isolating it. We need to get it by itself so that we can actually see what it needs to equal, isolating n. So let's divide both sides by m. Let's get m to the other side. We end up with this. Then let's get x to the other side. If you can't remember how to do a division with a fraction, it's 1 over m divided by x, which is kind of like saying x over 1. So we do that high school flip and multiply rule. Maybe that doesn't help people, but it sure helps me. So we end up with 1 over x times 1 over m equals 1 over xm. I find that very helpful. So after we divide by x, we end up with 1 over xm less than n. So now we've isolated n. And at this point in time, since we've isolated n, I'm very happy to put that x value back in because now we need to work with all the numbers that we actually have. Replace x with its value, right? I had assigned x a value earlier. Now we're going to replace that back in. We end up with 1 over, and this is why I did it, because I found this personally just so hard to follow. 1 minus 1 over n squared, m less than n. So what we're going to notice here is we're going to notice that as n gets bigger, that shouldn't really be a capital N. We're talking about the variable lowercase n. We're going to notice that 1 over n squared gets smaller. It's going to keep getting smaller. So what does this tell us? This tells us that we're going to need to pick a value of n that keeps us in the positives. We want to stay positive. So if we pick n equals 1, this is I'll switch colors again. We're going to switch to green being like that icky choice. So let's pretend for a second that we let n equal 1. Then we'd end up with this on the bottom, which is going to be 1 minus 1, which is going to be this, which is going to be this. And we cannot divide by 0. That's not good. That would be like taking this whole thing and making it 0. So picking n equals 1 is not going to be a good value for us. Okay, what happens instead if we pick 1, n equals 2? If we say n equals 2 on the bottom, we can most definitely still end up with now something that's a little bit more appropriate. We say 1, this is going to be 1 over 4, right? This is much more appropriate. I can just do it like this. So what we can tell by looking at it like this is that n is definitely going to want to be greater than 2, right? We want to be able to keep pushing that value up. Now, yes, in theory, this does work, but we still have one more case that we want to just discuss for a second. So let's just add here. So therefore, n needs to be greater than 2. We're going to pick this ensures that we're going to be 2.1, right? Yes, n equals 2 works, but what we're going to attempt to do here is ensure that it works for multiple situations. So let's look at just one more situation here where we want to make sure that this is going to be fine. Since we made sure that we weren't going to end up with a 0 by saying that n was going to be greater than 2. And you'll see why we don't just say greater than 1. in just a moment. We're going to add that plus 1 back in somewhere else. Now we're going to make sure that we don't end up with a negative either. We don't want a negative, so let's consider the situation where we are between that 0 and 1. What does that mean for us? Well, again, if we said that 1 is going to be like this, which is going to be like this, which is going to be like this, 0.75. That's kind of a big, that's an annoying number to work with. What if instead we say something like n is 3? And we do 3 squared, 1 over 9. And then here we end up with like, I don't know, whatever 8/9 are as well. Right? We'll see that as n increases, we see this gets closer to 1. That's great. That's a good thing for us, because what we can then say is that all of these values, that as n increases and this gets closer to 1, that means, and given the minimum value we're allowing it to be, right, 2.000, whatever, 1, whatever we're allowing that minimum to be, these values, 1 over n squared, will definitely be greater than, oops, or equal to a half, right? We can see that these values are bigger than a half. If we allow ourselves to get really, really close to that value of 2, there's just no way that we're going to ever be smaller than it. We can see that 1/2 is definitely less than this entire term here. So that kind of allows us to do some magical math hand wavy things. Sometimes I like to draw just the magic that's happening around what we're about to say. Because we're going to say that this then, 1 minus 1 over n squared is like approximately equal to a half. It's definitely not going to be less than that. So we're using that rounding up trick that we saw before, because what this means is we can basically say, if we can prove it's true for something as small as a half, it's going to still be true for those bigger values as we're working toward it. And we can say that again because of what we originally were looking at. Where is it? Right. Whoops. Right here. Because we originally said we're looking at those n values greater than 0, if it's going to be true for a half, and a half is smaller than this, and a half is smaller than this, then there's a good chance that we're actually going to be okay here to say, if it's true for a half, it's 1 minus a half. It's going to be true for the values that are even closer to 1. So that's kind of the trick that we're going to use there. All right, so armed with that trick, let's replace this right here with our new value. 1 minus a half is just going to be a half. So let's go ahead and do that. 1 minus a half. This is like this. Make sure I didn't mess that up. Good. And then that's the same as this here. 1 minus, 1/2 m, which is less than n. And when you do all the same denominator business that we need to get going on over here, so we multiply both sides by m, and we do our cross multiplication, and we get this whole term sorted out properly. I'm not going to do all of those. What we end up seeing is basically we end up just flipping it. So it looks like this. So we have now determined 2 different scenarios that as n gets big, we can say something like, where did we write as n gets big? Right here. As n gets big, we can say something like n needs to be greater than 2. But in the case where n might be small, we might need to consider a different value. So since we don't, I'll write this down. So we don't want n less than 2 over m to avoid negatives, right? We don't want those negatives in there. So that's why we're going to avoid that. And previously we said we do not want n less than 2 to avoid the 0 on, or not on, in the denominator. So now how do we frame n so that both of these statements can be true? We're going to need to take a max, and I might even want to write the word max in. So what we've now determined, and then we'll do that plus 1, since we are saying it's going to be strictly greater than 2, strictly greater than 2 over m, right? That was what we said here, strictly greater than 2 over m. And up here, we had said strictly greater than 2. So we add in that plus 1 over here to help us with that scenario. So what have we said here? We've said that if we end up, and the reminder here is also that we're doing both of these because if m is big enough, we don't care anymore about it. As long as m is a big enough value, meaning greater than 1, so 2 or greater, this works out just fine. And if m is smaller, if m is between 0 and 1, we need to actually factor in m. So let's just really quickly look at both of those two sides here, just very, very, very quickly. If m is greater than or equal to 1, this term over here becomes 2 or smaller. So in those situations, we end up using this value here. But in the situation where m is going to be between 0 and 1, this value is going to be small. 2 over anything less than 1 will be bigger than 2. So then this is the term that we end up using in those situations. Okay, so now we have found some possible x value that we do think will work based off of taking that inequality and sort of setting ourselves up for success there. So let's actually officially start our solution. Let n equal the max between 2 over m and 2 plus 1. This is how we always start our proofs. This is our official, formal proof, whatever you want to call it. How annoying of me to do my line like that, but whatever. This is where we're officially kicking off our proof of why this is going to work, why this value is true. Okay, let's get into this trick here. So the other thing we're going to want to make sure we say is we need to actually make sure that we just say that m doesn't matter, right? And actually, since this uses m, I'm going to define my m first. Let m greater than 0 be an arbitrary number. And we can even say in the set of reals, be nice and specific there. What are we actually trying to do? We will show that given 1 and 2, that n is going to be less than our original value. That's what we're going to try and show here. So given our definition of m, we can go ahead and say, given our definition of n, it implies n is going to be strictly greater than 2. And I can say that because if n takes the max 2, depending on what m is, right, that arbitrary value of m, if n is max 2, we have this plus 1. That's definitely going to push us up over 2. We can say that n is definitely going to be greater than 2. So knowing that fact, we can also say, therefore, 1 over n squared is going to be less than 1/2. This is that round up trick that we saw previously. So just quickly, the side note here is, again, if we're saying that n is strictly greater than 2, just for our purposes, let's even make it say 2, because it would be like 2.1, 2.0001, whatever it might be. A reminder of what that was going to look like was something like, oops, this, and this is definitely less than this. One more time, we can say it like this is also going to be strictly less than this. So we can see that that's a true statement there. We can say that 1 over n squared is definitely less than 1/2. So that's great news for us. Okay. So using that, we're going to sort of just hold on to that for a second. It's nice that we've given this a number because we're probably going to want to refer back to this piece of information later. Let's do the next one here. We can also say that our definition of n, because don't forget, it's that max function. So given 2, it will also imply that, whoops, n is greater than 2 over m. And so if we do some rearranging here, what we're going to see over here, that in this scenario, we can say m over 2 n is greater than 1. So all I did was uh, multiply both sides by m, divide both sides by 2, and we ended up getting this nifty value right over here. Oh, I don't like that those lines like get darker when they color over each other like that. It's distracting there. Okay. So when we combine these two observations, this is what we're going to get. Combining 3 and 4, we see that m n squared minus 1 is the same thing here. Now, a reminder what we were able to do here, we factored out that n squared. So it's going to be the same thing as this, which, there we go, we know is going to be greater than m squared over 1 minus 1/2. This here is true because of step 3, just in case you were forgetting why that's true. This is then equal, oops, oh, my eraser just randomly showed up there. Let me move all this over so I can keep this all in the same line as much as possible anyway. Sorry. This is then going to be equal to m over 2 n squared, which is greater than n. We also, in order to get to this value here, I better do this with the laser pointer. In order to get to this value here, all I did was take this over here, and it's like this. And we can say m over 2 times n squared. So that's how we managed to get to this value here, is that was just using like arithmetic. And then we're able to say that this here is true because of 4, right? Because 4, if we were to multiply both sides, of 4 by n, we would get m over 2 n squared is greater than n. So that would follow that m over 2 n is less than 1, right? If we go right here, we add n to each side or multiply n into each side, it looks exactly like what we're talking about below. So that's why I'm able to say that. So what we've now concluded, so all written in one line here, we have now shown that this is the case. And that was indeed what we said we were going to try to prove, that m was less than that big term, n is less than that big term. We did it. Now, the part that seems to be tripping a lot of people up when it comes to this rounding up trick that we've been doing is that we have to remember, and the rounding up trick being like step 3, what we have to remember is if A is less than B and B is less than C, then A is less than C. That's another A. This is the key to the rounding up trick that we are showing above. Rounding up trick. So when we said something like 1 over n squared, when we said something like given n is greater than 2, 1 over n squared is definitely going to be less than 1/2. We were able to say that because when we factor in that n greater than 2, 1 over n squared is going to be less than or equal to, actually it will be strictly less than a quarter, right? Because we're strictly greater than 2 makes this strictly greater than 1/2, which means this is going to be a quarter, which is less than a half, which then implies that 1 over n squared will be less than a half. And that's how we're able to use the rounding up trick. It's using that logic of if A is less than B and B is less than C, then A will also be less than C. And this, just for those of you who are looking for extra math to do, this if-then statement can absolutely be proven to be true. I'm not going to do it right now, but just know that if you make this your P, you make this your Q, if P then Q, you can walk through a truth table and see that that is true. So if A less than B and B less than C, A less than C, we can maybe, hopefully, fingers crossed, start to see why we spend time doing truth tables before we make our way over to solving these proofs, and how we're going to use that information to do something like this roundup trick and other tricks that we've started to work into our proofs. All right, thanks everybody. Stay tuned for more exercises following this same general format, getting that max function into our n value and seeing how we can use that as we move toward asymptotic notation and understanding how this all sort of relates back to computer science. Have a great rest of your day, and I'll see you in the next one.